All right, welcome to Chapter 8, Section 1, called Volume of Cylinders. This is for Math 8. So a couple things you'll see on your screen here. The first thing you should see as a student is the due date. I don't see that on my teacher preview here, but you will see it on your student screen. The second part here is attempts. You always have unlimited attempts on homework, tests, and quizzes, so you can come and do this as many times as you would like. Number of questions just tells you how many questions are on this particular assignment. Grading policy is always best score, so whichever attempt is the best one is the one you keep. And partial credit is enabled. So if you answer 1 or 2 questions correctly, you get credit for your one question, or however many you answer correctly. Down here it says once you start your homework, you must finish it before you can work on anything else. And what that means is once I click start, down in the bottom right corner here, we will see a submit assignment button. I don't see it on my teacher preview, but you will see it on your student side. So when we want to leave this screen, whether or not we have finished any of the problems, or maybe only one of them, if we have a green check mark, it saves our place. But we want to click that submit assignment button, because otherwise if we just close the tab or close our computers, Alex will assume that we want to leave this attempt open. Remember, you have unlimited attempts, and it's going to save your place as long as you have that green check mark. So there's no reason to leave it open. It will lock you out of all your other assignments, just like that first screen said, if you don't click submit assignment. So that's one big reason to click that button. The second one is that it will affect the grade book, and your teacher can actually see what you've been working on once you click that submit assignment button. Before that, it's basically just paused. We don't see anything. So good idea, good habit. Click that button every time you want to leave. On the side here, you can see we have calculator. That's not always open, but it's here right now. Explanation, example, and message center are always there. So explanation tells you you're going to lose your current question attempt because it's going to give you the solution to this question. So you don't get the, they're not going to give you the answer and then let you come type it in. Example will give you an example of what it is we're going to be doing for this problem. It'll walk you through one very similar to this. You can close this example when you're ready. You can open another one if you want to see another one. You can also message your teacher directly from this screen. And it attaches a picture so we know where to come help you. All right, let's go ahead and get started on here. Before we jump too far into these ones, because we're kind of jumping right into three-dimensional objects without really looking at the three-dimensional objects. So I know we did this in class. If you come to class with me, and I know with quite a few of the other centers, we're going to be doing something along the lines of we're going to give you some cutouts and kind of have you explore what you notice about some of these three-dimensional objects. Because it's a little easier to think about them if we can actually see them or hold them even. And I know on this one we can't necessarily hold it, but we can kind of see. So we're going to start looking at a rectangular prism. That's kind of the easy one to start with. So, and rectangular prism, if you can see this guy, so if I let him spin, it's just a box, right? It's a regular old box. Kind of looks a little crazy with the red and the green lines there, but it's just a box. And this is what we call a net. Meaning if I opened it up, here's all the sides shown. And if I click play here, I can even see it's going to close the box for me. So it's going to fold up the sides, and there we go. We have our rectangular prism. So, and then it's opening back up. So I can see the net is just the sides of the box kind of unfolded. What would I see if I completely cut it open and unfolded it? So this is a rectangular prism, very common one. Triangular prism, that's another one. So it's kind of another box, but it's a very funny shaped box. So it's triangular. And we call it a triangular prism specifically because we have a triangle, and a lot of the time when we're looking at it, it would be flat like this on the ground. And so the base, the bottom and the top of this guy are triangular. That's why we call it a triangular prism. Rectangular prism, that had rectangles for the top and the bottom. In this case, it was a little bit more square. That looks a bit more square to me, but we still call it a rectangular prism. With this one, we call it triangular. So on the net, I can click play again, and we can see it folding up, and we have a triangular prism. And in this case, they have the sides triangular, but we can kind of see it's making this kind of pyramid shape almost, but it's not a true pyramid. Pyramids come to a point at the top. This one has a line on the top, so it's a prism. There's a few other ones here. We don't really deal with pentagonal or octagonal prisms, but again, it has to do with that shape that's on both sides there. So octagon on this side, it's a pentagon on the pentagon. So you can see it's named by that shape. All the other sides, if you notice, are all squares or rectangles. Going through here, if I click play again, and it unfolds, and then I let it turn side. Oh, I wanted to turn sideways. Well, that's good enough. So you can see that these are either squares or rectangles going down the middle for each one of these guys. It's just that the two sides opposite each other, which I'm calling the bases, are some other shape, and that's how we name a prism. So we also have other shapes. So we have, this is a cube, and I don't know if I've necessarily drawn it this way, but we can kind of see as it closes, it kind of closes a little funny on this one, but we can see that it makes a cube. Normally I draw this a little bit more like what this guy looks like, where you draw it like this. They're all just squares. So this is kind of a funny net to me, but it's still a net. The cone, so this is another shape. We have a cone. So with a cone, it actually kind of looks a little different here. I can kind of move this around a little so you can see it. So it's got this a little bit more than half circle, but this kind of funny shape with a circle on it. Because a cone has a circular base. So I can kind of can I rotate this guy around? Yeah. So we can see it's got a circle on the bottom, right? So the top is that funny shape, and it just comes together on the circle. A cylinder. So a cylinder, we have a can, right? Some kind of can shape. And we can picture maybe this is like a can of green beans or something. And we can open this guy up by kind of cutting it right down the side, and it splits open, and we can lay it flat. And now if we look at this, we have a rectangle with two circles. And we can calculate information based on the rectangle and the two circles really easily, because we know the area for a rectangle's length times width. We'll review the area for a circle, because I think, again, we're kind of jumping into this chapter. But we're going to be dealing with cylinders in this one, so this one's definitely a big one. But when we're looking at nets, we're just saying, if I were to cut it open and flatten it out, what would it look like? So in this case, a lot of the time, it kind of looks like a division symbol, right? If we actually turn it this way, it looks like a kind of wide division symbol there. We also have other, shapes on here. So this is actually a pyramid. So I can actually close this guy up, and you can see this is a pyramid. So I don't think I can move it around at all, but yeah, for some reason I can't scooch this guy around like I can the other one when I'm looking at it, but I can definitely see, and the net, so we can see the net here when it flattens out. All of a sudden I have four triangles with a square at the bottom, and we call this a square-based pyramid or a square pyramid, because the bottom is a square. If it was a triangle, it'd be a triangular pyramid. If it was a octagon, it'd be an octagonal pyramid. So again, they're named by that shape, that base shape. But this is a true pyramid because it's got that point at the top. So even though that other shape on here kind of sort of looks like a pyramid when they close it up, because they had it closed like this, it's got that line on the top. That means it's not a pyramid. This is a prism, because it's actually a box-ish shape. All right. So I think that's enough. We'll kind of switch over back to this guy. I just wanted to go over those shapes, because without really taking a look at a lot of those shapes, we don't realize kind of what they would look like if we opened them up. It's just not something we kind of think about very often. So on this one, we have a cylindrical construction pipe. So a cylindrical pipe means that it's a cylinder, right? Kind of just like that can of green beans we were looking at a minute ago. So they tell us that the radius is 2.5 feet. If the pipe is 21 feet long, what is its volume? So we need to know a couple of things here before we can move forward. And they also tell us to use the value 3.14 for pi. So we're going to use pi in our formula, and we're going to switch over to my whiteboard here so we know that. This is a rounded number for pi. If we actually, do they have pi on the calculator here? Let me see if they have it. Doesn't look like they even have it here. If they did have pi on the calculator and you click pi, it's a number that never ends. It's not repeating, but it's not terminating either. It continues on and on and on forever, never ending, and numbers are always changing. So they round it to make it simpler for us a little bit. Sometimes they'll also have us use a fraction. I've seen a fraction also. All right, we're going to kind of jump in here. So the tank, or in this case, it's a cylindrical construction pipe. And we want to know the formula for the volume. And again, if you click on example, they'll show you these things because they're going to give you something similar. So in this case, it's a water tank. Not really a big deal. It's kind of the same idea. Doesn't matter necessarily what the item is, as long as they're both cylinders, we can use the formula. So this is the formula we want. Volume equals pi r squared h. And we're going to break this down just a little bit, because a lot of these actually come from the same type of formula. No matter what we're using, what we do is we find the area of the base. In this case, it's a circle. So we find the area of the base, and then we multiply that by its height, however tall it is. Because we can kind of think of that, and I'm not very good at drawing this, but we can think of that as there's multiple kind of layers in here. And so each one is whatever unit this is, which is feet. So each foot has the same area. We're basically kind of looking at each layer when we multiply it. And I know that was a very horrible little drawing of that. I'm not very good at that part as far as drawing it, but that's kind of the idea. So the area of a circle is pi r squared, this guy here. So this is the base, and we represent that with a capital B times h. Well, in almost all of our figures here, this is the formula that we use. Base times height. Whatever the base is, whatever that area formula is for the bottom or the congruent sides, I guess you could say. So in this case, they're both circles. Those are my bases. That's what we're going to use. We're going to use the area for whatever that shape is and then multiply by the height. So that's where pi r squared h comes from. All right, so let's go ahead and start plugging this in. So instead of pi, they've asked us to use 3.14. So I'm not even going to write pi anymore. I'm going to write 3.14 times the radius squared. So they told us the radius was 2.5. If they gave you the diameter goes all the way across the circle, but it goes through the center. So that's important. A radius goes from the center to the side. This is a radius. A diameter goes from side to side through the center. So it actually has 2 radii in it. So if they give you the diameter, you just divide by 2. That's kind of the idea there. Just pay attention to what number they're giving you. They gave us the radius, so we don't have to do that dividing by 2. And then the height of this one, even though it's laying down on its side, we still consider this the height. I know it's a little bit more like the length, but we say the height. All right, so we have our pieces. Oh, and I forgot to put squared there because we want to square the radius. That's how we get the area of the circle. Pi times the radius squared. And then we multiply that by the height because we can kind of divide this up into 21 different layers. And each layer has this area in it. So, all right, so we have the 3 didn't go in. 3.14 times 2.5 squared. All right, so this is the area of the circle. I don't want to round in between anywhere. I need to wait until I get to my answer to round. Don't round within the problem. When they say round to the nearest whole number, wait till the end. So I want to multiply this by 21. Why isn't it doing it? There we go. So now I can think about rounding. So if I want to round to the whole number, that means I'm going to get rid of these decimals, but I need to decide, is this number going to round down to 412 or up to 413? So I look at this very next number and go, oh, that's 4 or less. 1 is definitely less than 4. So it's just going to round down to 412. So we have 412. They also tell us to be sure to include the correct unit in your answer. They're not doing that for us. So remember, the unit represents the number of dimensions we're using. So with area, area is kind of a length times width. I know it's not perfect for a circle, but that's the idea of 2.5 squared. It's kind of a length and width. We're kind of cutting off the parts of the square there that it would be on. So this is a little bit like length times width, and this is like height. So this is 3 dimensions. We can also consider that each one of these has a feet on it, except for the 3.14. So this would be feet squared, because feet times feet is feet squared. This is another feet, so we end up with feet cubed. Again, 3-dimensional. So we want to make sure that we click feet cubed. If it'll let me click it. Why isn't it allowing it? Let me scroll over. That's why. All right, so let's go ahead and check that guy. Perfect. All right, we're going to go to the next one. All right. So on this one, we need to pay attention to what we're being asked. So they're kind of asking us to go a little bit farther on this one. The company makes steel rods shaped like cylinders. So we're still working with cylinders. So remember, it's still that kind of can looking shape. Each rod has a radius of 2 centimeters. So if I draw a cylinder, and I'm not great at drawing cylinders, but we're going to pretend like I am. So here's my cylinder, 2 centimeters. It says radius of 2 centimeters and height of 60 centimeters. So it's this kind of side length is 60 centimeters here. How much steel will the company need to make 192 rods? And again, use 3.14 for pi. Do not round your answer. So this time we do not round it. Make sure you're following those directions. If it says to round it, round it. If it says not to round it, don't round it. That will get your answer marked wrong. And I've seen that happen quite a few times. Okay, so for this guy, they're not asking us what the volume of the rod is, but we're going to need the volume of the rod to answer this question. So we're not going to type the volume in here. That's not the answer. But we do need to know how much centimeters cubed each rod is if the company wants to make 192 of them. So we need to know how many is each one, and then we can multiply that by 192 to find out how much we need to make 192 of them. But I need to know how much each one is before I can do my multiplication, right? So I'm going to need to use the volume. I need the volume to figure out how many or how much total steel I need. I know how many I want to make. I know how, the radius and the height of this one. So I need the volume for this. So we're going to use pi r squared h again. Same formula as before. So I have volume equals 3.14, because that's what they asked me to use for pi. The radius is 2. That's squared times the height, which is 60. All right, so let's go ahead and do this. We have 0.14 times 2 squared times 60. We can type this all in at once. We don't need to do it in pieces like I did on the last one. I was just making a point that this is the area of the circle, the ends. So this is the area of one of the ends, and then we're going to multiply that by 60, because we could divide this up into 60 layers, and I know that's not nowhere near 60 layers, because I'd need a much longer picture to be able to do the 60. But that's the idea. There's 60 layers, each with that same area. So we're going to get V equals 753.6, and this is centimeters cubed, 3-dimensional. Volume is 3-dimensional. This is not the answer we're going to type in. This is the volume of one rod. How many rods do we want? 192. So we need to take this calculation and go times 192. That'll tell the company how much steel we need to make 192 of these rods, each with 753 and 6/10 centimeters cubed steel. Sorry, that sounded really funny. It's kind of run on there. So it's not volume anymore now. I'm answering the question. Let's see, it's a nice big number here. So I have a comma. So we need 144,692 and 2/10 centimeters cubed steel to make that many rods. So something like this could be used to, a company for ordering. Well, if we have an order where we need to get this many out, how much steel do we need to order so that we can make the correct number, so we can get our order out in time? So this is definitely a real world question, that companies will use. I know I've seen this one quite a few times where it's more asking about how much would it cost. They'll tell you, it costs this much per centimeter cubed. So how much would the rod end up costing? Something like that. So there's definitely a few different versions of this one that I've seen, but it's taking that extra step. I have the volume. Now what are they asking me to actually do with the volume? So just make sure you're paying attention for this guy. And they're giving me grief because I did not put my comma in. That's what they're giving me grief about. All right, so that was section 1. I will see you in section 2.